So for my project, I chose to focus on 3D bioprinted organs and its current applications and future projections. So my presentation is just broken down into what bioprinting is, how bioprinting is used, and bioprinting for the future. So regenerative medicine aims to repair, replace, or regrow diseased and damaged tissues. This is done through emerging technologies such as stem cell therapies, genetic and tissue engineering, and artificial organs. And of course, today I will focus on 3D bioprinting. 3D bioprinting works similar to conventional 3D printing. However, the cells and bioactive materials are used instead of resins and plastics. Cells are harvested from the patient, and biomaterials are used to create bioinks. The bioinks are then deposited layer by layer to build the organ. There are numerous approaches to 3D bioprinting that differ based on their method of material deposition, compatibility of biomaterials. However, the technicalities of these approaches are outside the scope of this presentation. So in general, there are 4 major steps to 3D bioprint an organ. CT or MRI images are first taken of the patient's current organ. These are then used to create a digital model, which allows the printed organ to perfectly match that of the patient. If the current tissue is damaged or disfigured, the organ can be virtually remodeled in the digital programs to create a healthy organ and to match the patient's anatomy. The second step is the creation of bioink and the harvesting of patient cells. Bioinks are gel-like materials that are added into and extruded by the 3D printer. They are used to create the structure of the organ, called the scaffolding, and consists of polymers, proteins, and growth factors. Additionally, cells are collected from the patient. Fat tissue or bone marrow can be modified into stem cells and then differentiated into the type of cell needed for the organ that's being printed. In some printing techniques, stem cells or differentiated cells are included directly into the bioinks. The third step is to print the scaffolding and to add the cells. So the bioinks are added into the 3D printer and the scaffolding is created based on the digital model. The scaffolding is important because it mimics the natural supportive framework of collagen, extracellular matrices, and fibrous tissues that help the organ maintain their structure and shape. After the scaffolding is printed, the collected cells are seeded or deposited onto the scaffolding. And the last step is growth and maturation of the cells in a bioreactor to create the fully functional organ. So current bioprinting is far from perfect. There are a multitude of challenges that bioprinting has to overcome before this technology can produce functioning complex organs. One of the major challenges is the actual complexity of organs. For example, the kidney is made up of approximately 26 different cell types, all arranged in intricate structures that can be difficult to replicate. The second big challenge is creating extensive vascular networks. Proper perfusion of blood to all cells is essential for delivery of oxygen and nutrients and removal of wastes and metabolites. Without a proper blood supply, these organs would not be able to function inside the body. This is a limiting factor to how thick you can make printed tissues. And the third challenge is that the organs must be physiologically functional. So the kidney is our example. In addition to being able to filter out waste and water, it also has other physiological components in order to make a fully functional kidney. And now we will move on to how bioprinting is used. So current research is applying this technology to print hard tissues like bone, simple organs like bladders and corneas, and complex organs like hearts, kidneys, and brains. Transplantation of 3D printed organs is still limited to clinical trials, and no mainstream options are available on the market yet. Corneas are expected to be the first 3D printed organ to become widely available on the market. Printing corneas is a lot more straightforward than printing other organs because of the simple layering techniques to place the cells. They're also relatively small compared to other organs, and they don't require vasculature. And this is a picture of a 3D printed cornea from a regenerative medicine startup called Precise Bio, who expects to have mainstream cornea printing within the next decade. Complex solid organs like hearts, kidneys, and brains are much more difficult to print and design due to the challenges I mentioned previously. This research group here created a miniature heart that completely matched the cellular, immune, and chemical characteristics of the patient. The left image is the 3D model of the heart. The middle two are the heart being printed in a hydrogel structure. And a hydrogel structure is kind of like a substitute for scaffolding. It keeps the cells in place and where they need to be so they can grow properly. And the right is a picture of the extracted heart. The left and right ventricles were stained with dye to show perfusion. This print is significant because the heart contained the appropriate chambers and structures and was able to perfuse properly, which is further than any other research group has achieved. Although this heart cannot beat, and it was approximately the size of a rabbit's heart, this demonstrates significant progress toward viable bioprinted hearts. And eventually, we will have the ability to produce personalized 3D printed organs for any individual that needs one. This has the power to solve numerous clinical and medical issues applicable to our world today. So currently, we have a severe worldwide organ shortage, and unfortunately, many people die while on wait lists. Bioprinting will reduce mortality and wait times for an organ while increasing the quality of life for these individuals. Another key advantage of bioprinting is the personalization aspect that you can do with the organ. Since the patient's own cells are used to create the organ, the risk of rejection is nearly diminished, and the recipient will not have to take lifelong immunosuppressants to prevent rejection. This technology can also be applied to drug discovery, drug testing, and toxicity studies. And bioprinted skin can be used for cosmetic testing in replacement of animals. This overcomes a lot of ethical issues regarding the use of animals in medical testing and cosmetic testing. And next we have bioprinting for the future. So there's 4 main future projections I'd like to discuss today. And the first is anti-aging and a disease-free future. So readily available bioprinted organs will be the future of living longer. Aging organs will be easily replaced, and this procedure could become as normal and popular as current cosmetic surgeries like nose jobs. This does beg the question as to how much longer we could actually extend our lives by maintaining optimal organ age and health. Additionally, bioprinted organs are a strategy to completely eliminate organ-related diseases since we're able to replace the diseased organs. Overall, this will greatly improve quality of life and can greatly improve the human condition. The human condition is the experiences and events that kind of make up human existence. So in terms of modifying the human condition, the development of cancer, organ failure, or disease will no longer mean pain and suffering for individuals and their families. And the ability to live longer and at peak function will allow humans to accomplish more within a lifetime. This has the potential to change our perceptions of our own mortality and what it means to be human. This technology may also be applied to perinatal and infant medical care. While genetic testing gives us the opportunity to kind of figure out if a child may be born with an organ defect, bioprinting can be used to help us overcome these challenges. For example, congenital heart disease is the most common type of birth defect. If genetic testing or fetal echocardiograms demonstrate that a baby has congenital heart disease, a healthy organ can be planned and printed in anticipation of the delivery date so that the baby can receive a new and healthy heart immediately. And this does raise the question that if our perceptions of individuals who are differently abled will shift. And although a healthy and disease-free society may be an ideal future outlook, there needs to be acceptance from the general public regarding this technology in order to achieve this utopia-like scenario. From a utilitarian approach toward ethics, quality of life is valued, and actions that increase quality of life is viewed as morally right. Therefore, utilizing 3D printed organs to improve quality of life and reduce suffering and reduce mortality is morally right and acceptable. However, for some individuals and in some cultures, hardships, pain, and suffering is an integral part of the human condition. For some, this suffering and pain may be seen as an opportunity for self-transformation and spiritual connection. 3D bioprinting will greatly challenge these perceptions, and there's a likelihood that some individuals may not be receptive or accepting of this technology. Public ethics or public opinion will likely play a role in how this technology progresses and how regulatory processes are framed. The second future projection is one of post-scarcity abundance or lack thereof. Post-scarcity abundance refers to a predicted far-term future scenario where most goods are in abundance and the needs of all are met. This may be applied to 3D bioprinting, where technology will become so cheap and commonplace, and AI and robotics will become so advanced that organs can be printed in abundance for little to no cost for patients with minimal human involvement. This will further allow humans to live longer and disease-free. However, a post-scarcity future will take longer to develop compared to the time 3D bioprinting will be available to us. In the near-term future, I have little doubt that private companies and clinics will capitalize on this technology in the meantime. Anti-aging is currently a billion-dollar industry, and bioprinting will definitely feed into this. However, privatization does raise numerous concerns of accessibility for individuals of lower socioeconomic status and classes, especially in countries where universal healthcare is lacking. Currently, differential access to healthcare based on gender, income, and ethnicity is a prominent issue in healthcare systems. These disparities will only be exacerbated if wealthy individuals are able to live longer and healthier lives, while less affluent individuals struggle to receive life-saving treatments. As this technology advances, this is something that needs to be taken into account, and proper regulations must be established by healthcare and governing bodies to ensure equal access to this technology. The third future projection is enhanced organs and transhumanism. So in the future, medicine will be focused on human enhancement. 3D bioprinting can produce organs that allow humans to exceed our natural capabilities. The cells from a patient could be genetically modified before being used to make the bioprinted organ. This can not only prevent later diseases from developing, but it can also increase the efficiency of the organ, for example. So enhanced hearts or lungs could have more efficient metabolisms or refined oxygen consumption to improve a human's physical output. We could have the ability to become faster, stronger, and healthier than ever before. These enhanced bioprinted organs, what a human is able to achieve and perceive with an extended lifetime. Additionally, completely new organs could be created that enhance humans' ability to function and perform tasks. For example, if a person used a robotic prosthesis or they had electronic implants, an organ could be created with modified cells that produce energy to power these prostheses or implants. And this feeds into the philosophical movement of transhumanism. So the transhumanism movement believes in improving and enhancing mood, intellect, longevity, and human capabilities through the merge of humans and technology. And bioprinted organs will likely play a key role in achieving this type of future. For example, smart contact lenses that can display augmented reality, increase vision acuity, and allow our eyes to zoom into objects similar to a camera are already in development. Implantation and integration of this technology while a cornea is being printed will allow a unique merge of our biological systems with robotic counterparts in order to enhance and improve human abilities. Different implants could also lead to a new era of personalized medicine, where electronic or robotic implants could help us track physiological data like heart rate, nutrient intake, water intake, and glucose or insulin levels. The merging of 3D bioprinting and transhumanism is definitely an innovative and exciting future that should be considered. And lastly, 3D bioprinting could support spaceflight and off-world travel. If an astronaut is on a long space flight or off to another planet, they are not able to turn around or return to Earth for medical attention. The ability to print personalized organs on demand in response to health concerns or emergency situations will greatly increase humans' ability to survive and flourish in space. The concept of enhanced organs could also be extended to space. Organs that are resistant to radiation could be created, and maybe we'll even create lungs that can breathe Martian air, who knows? And pictured on the left is a concept for a space 3D bioprinter from NASA. In summary, the advent of 3D bioprinting will solve many current-day medical challenges, reduce mortality, and increase quality of life. Future use of bioprinted organs will allow us to live longer and disease-free, yet also challenge what it means to be human. Overall, the future of 3D printing is exciting and promising. And that is the presentation.
Great. So what I guess one might ask is how far are we from actually realizing this? And I guess in the areas of skin, cartilage, and bone, we could probably do 3D printing right now of things of various shapes and so on. Mm-hmm. But ordinarily, we don't need to. I mean, those are areas where regenerative medicine is sort of routinely used now, but it's just not very exciting because they aren't very complex organs, and you wouldn't need the part that you're adding to be of a specific shape, because if you think of just sort of sprinkling the cells, it would probably work just fine to kind of sprinkle the cells and have them fill in the defect. So in a sense, one could do what you're talking about right now with skin, cartilage, and bone, but you don't really need to. Mm-hmm. With more complex organs, it's different from organ to organ. Now, I'm more of a kidney person than a liver person, but my impression is if you kept the cells of a liver alive, sort of in random order, it would the organ would still do useful things. It wouldn't be as good as a regular liver, but it wouldn't be completely worthless. Whereas the kidney, the cells really have to be sort of in series. They can't just be random, like these kinds of cells followed by these kinds of cells, different regions of the kidney and so on. So it is probably likely there that we would accept some shortcuts, and it's kind of amusing to think about this. Like a lot of people working on planning the sorts of things that you're talking about are thinking that in the kidney, maybe the 3D printed kidney wouldn't be able to actually concentrate the urine. So you can figure out other simple ways to concentrate the urine in some other, device. So, and the reason for that is it's so darn hard to make those long loops of Henle and that medullary gradient of the outer medulla, inner medulla, and to avoid washing out the gradient. It's kind of cool how specially designed that part of the kidney is, but it's very, very hard to reproduce. So quite a few years ago, people working in that field thought that they would kind of give up on making a kidney that can concentrate the urine as well as a normal kidney. Just say, well, we want it to do all the other things, but it doesn't have to do that. And so if it doesn't have to do that, it doesn't need the long loops of Henle and the specialized osmotic gradient and so on. So we'll probably end up with other compromises. I'm simply describing the ones in the kidney because I know that better. But so there'll be kind of a long transition period where we're using 3D printed organs, and they're very, very useful, but not quite as useful as the real organ would be. But then, of course, we'll reach a point where they are just as good as the real organ, and then finally where you can make them better. You can put in gorilla heart or elephant heart or something where that's much better than a normal heart. And so that person will have much greater endurance and be able to do all sorts of things that normal humans can't do. So over maybe 50, 60 years, you see all these various phases of 3D printing kind of playing out. So the graphic that I'm using here, this is showing, let me just see if I can, gallery. Yeah, so it's a very fanciful thing, but it's a living woman over there, and then the printer is printing the woman right beside. So I think it's going to be a long time before
that's going to be a while, but
we're able to do that. But it's interesting conceptually. Anyway, and of course, 3D printing is only one way to do this. Another way is to decellularize existing organs. So you then have the substrate for the cells to grow into and so on. But it's hard to get that exactly right. It's hard to remove all the cells without also removing part of the substrate that you kind of need, and mediators that help the right kind of cells find their proper location and so on. So it's interesting to think that maybe there would be a third way where you could program in exactly what you need and have a very high resolution 3D printer that also can have all the mediators and that sort of thing. So it's not just the cells, but also getting the environment for the cells that have all that be completely correct. And the thing about that is it would kind of require us to know everything about the normal condition so we can recreate that. Of course, that's difficult. We don't really have all all that information
Mhm.
now. So we don't know quite what the requirements are to make everything, to make the matrix of the organ, the stuff around the cells,
Mhm.
completely normal. So there are all sorts of challenges there, but it's
Quite a few, yeah.
nice to think about it. Okay, well, thank you very much, and so I think that's it for now. And yeah, so you'll be sending your paper too?
Yeah, within the hour. I'm
Yeah.
just finishing up
Yeah.
the citations.
Okay, well, that sounds
Yep.
great. Thank you.
Perfect.
Thank
Thank
you
you very
very
much.
much.
Have a
Okay.
good evening.